All right, let's just jump right in. You've probably been there, right? You switch doctors, you show up for your first appointment, and crickets. They know absolutely nothing about your medical history. It's so frustrating. You'd think in a world this connected, this would be a solved problem by now.
And, the easy answer is to blame bureaucracy or paperwork. But that's not the whole story. Not even close. At its heart, this is a massive, fundamental data problem. And honestly, cracking this nut is the key to unlocking the entire next generation of medicine, especially medicine powered by AI.
So, that's what we're going to do today. We're going to pull back the curtain on all that chaos. We're going to look at this incredible, unseen engine that's being built right now to bring some clarity, to get our health data ready for the kind of AI that's already changing everything.
So, here's the game plan. First, we're going to dig into why health data is such a mess to begin with. Then we'll see how we're building these, let's call them digital bridges, to connect everything. After that, we'll get into the really cool part, creating a universal language so these systems actually understand each other. And finally, we'll talk about the payoff and the pitfalls when you unleash AI on all this data. All right, let's get into it. Section 1. The chaos of health data. So why is medicine just so messy by its very nature?
This quote from Richard Dawkins just hits the nail on the head. He basically says physics gets to study the simple, predictable stuff. But biology, that's the study of the really, really complex things in the universe.
And just think about your own body for a second. It is not a simple machine, right? It's this incredibly complex, adaptive system. It's always changing. It's sensitive in ways we can't even predict. And let's be real, it's not always running at peak performance. Our bodies are just inherently messy. And here's the kicker. Because our biology is chaotic, the data that comes from it, it's just as chaotic. It's fragmented, it's disconnected. You've got pieces of it in a dozen different clinics, in 1,000 different formats. It's a giant contradictory puzzle.
Okay, so how in the world do we even start to clean up this mess? Well, the very first step is to build some digital bridges. We have to get all these isolated systems to finally start talking to each other.
The fancy word for this is interoperability. And that definition is so important. It's not just about swapping files back and forth. The key word here is use. Can the system that receives the data actually do something meaningful with it?
And this really happens on two different levels. First, you've got what's called syntactic interoperability. Think of this as the grammar. Do the systems speak the same structural language? Can they even connect? But the second level, that's the real challenge. Semantic interoperability. This is the vocabulary. Do they actually understand the meaning of the words they're exchanging?
Let's make this easier with an analogy. Imagine we're building a huge global library for all medical knowledge. Syntactic interoperability is just step one. It's like deciding that every single book and every single shelf everywhere in the world is going to be a standard size. That way, a book from a library in Austin will physically fit on a shelf in a library in Austria. The basic structure works.
But just because the book fits on the shelf, that doesn't mean you can read it, right? It could be in a completely different language. And that brings us to the next, absolutely crucial piece of the puzzle, creating a universal medical language.
I mean, think about it. How do you make absolutely sure that the term heart attack means the exact same thing, down to the last detail, to a computer in Austin as it does to one in Austria? Because if you can't do that, all the data in the world is basically useless.
When you go back to our library, what you need is a universal card catalog, a master index that defines every single concept once and for all. That is semantic interoperability. And the main tool the world is using to build this catalog is called SNOMED CT.
So what is this thing, SNOMED CT? Well, think of it as the most comprehensive, multilingual medical dictionary on the planet. It's already being used in over 80 countries, and the idea behind it is genius in its simplicity. Every single clinical idea, I mean everything, from sore throat to a super complex surgical procedure, gets its own unique ID number. It's basically a universal translator for all of healthcare. And this is how it works in practice. Let's take heart attack. A computer doesn't read the words. It sees that concept ID 222980006. That number means the same thing everywhere. Then you have the fully specified name, myocardial infarction, disorder. That's the super precise term for the clinicians. And finally, the display term is what the doctor actually sees on the screen. It's this elegant system that works for both machines and people.
Okay, so now for the payoff.
We've built the bridges, we have a universal language, the data is connected, and it's meaningful. So, what can we do with it? This is where we get into the really exciting stuff, the power and the peril of applying AI to all this.
I mean, the promise here is just huge. We're talking about using all this data to discover new drugs, to predict pandemics, to create medicine that's tailored specifically for you. But, and this is a big but, it is not that simple. Not at all.
Just take a look at this real-world puzzle with a diabetes drug called pioglitazone. In 2015, a massive study looking at data from 4 countries found 0 evidence that it increased the risk of bladder cancer. Okay, great. But then just 1 year later, another huge study comes out and finds the complete opposite. It did identify an increased risk. Same drug, tons of data, completely opposite conclusions. This is what makes medical data science so incredibly difficult.
And honestly, it gets even weirder. Let me ask you this. What if you had data that showed a new treatment was effective for men, and it was also effective for women? But when you combine their data into one big pile, the treatment suddenly looked like it was completely useless. Sounds like a riddle, right? But this kind of thing happens constantly.
This brain twister has a name. It's called Simpson's paradox. It's where a clear trend you see in different groups of data just vanishes, or even flips on its head the moment you combine them. And it is a massive, common trap when you're analyzing medical data.
And it's not just statisticians who can fall for this. Our most sophisticated AIs can learn the exact wrong lesson. There was this famous case where an AI was built to predict the risk of death from pneumonia, and it came back with a truly stunning finding. If you have asthma, you're actually at a lower risk, which, of course, is the complete opposite of reality and is just dangerously wrong.
So what on earth happened? Why did this smart AI get it so wrong? Well, it turns out that patients who have asthma and get pneumonia are considered so high risk that doctors send them straight to the ICU just as a precaution. And in the ICU, they get amazing, aggressive care, and so they have better outcomes. The AI didn't learn asthma is low risk. It learned going to the ICU saves your life. That's a true statement, but it's a terrifyingly misleading correlation in this context. And that brings us right to the big, final question we're all facing. We are building this incredible data foundation. AI is getting exponentially more powerful. The real challenge now is, how do we build the systems, and more importantly, the critical thinking to make sure these powerful tools actually help us and don't end up causing some new, unexpected harm? That's the tightrope we have to walk.